Hi, everybody. For the final half an hour, we've got a little practical, and a few slides where we talk about how we can use time series analysis tools with these time series. So I'm Matthew Gaddes, and I've spent my time as a PhD and a postdoc applying machine learning and deep learning to these time series of InSAR data. So to begin, I've taken a quick example. So I've taken Campi Flegrei, an Italian volcano. So that's Google Earth image showing whereabouts we are. And so if I wanted to approach this in a machine learning sense, my first port of call would be the COMET InSAR portal, so I can go and look and see what data there are. And if I had a look, I've zoomed in on this part of Italy, I can see that there's two descending tracks, so 022D, and then it sort of overlaps with 124D. So for some of these Italian volcanoes, if you're in that overlap region, you can process it from two different tracks. When you do that, so my normal workflow would be I take my LiCSAR interferograms and I turn them into time series with LiCSBAS. So if you do that for Campi Flegrei, on the right-hand side, you've got the velocity, so you can see a really clear deformation signal. There's a clear coastline and a few patches of incoherence on the land. If you use the LiCSBAS analysis tool, you can plot on one of these points and you can show the time history for that. So it's nearly linear inflation for this Italian volcano. Not completely linear, there's a few bits where it slows down and speeds up. And you can see it averages about 7 centimeters a year, 74 millimeters per year. So if anyone's got a rough idea on a back of the envelope calculation for this, if you've got 7 centimeters of deformation in 1 year, if you make a 12 or 24-day interferogram, I suppose that's 24, for a 24-day, that'd be 24 365ths of 7 centimeters. So you don't really get more than a few millimeters of deformation in a short temporal baseline interferogram. So what I show here is an interferogram that goes from in October 2014 through to December 2014. And you see there's not really anything to see in terms of deformation. And you can click forward going from December through into 2015. You might see some subtle atmospheric signals underneath the filtering. So let's see if I've got the cursor. These subtle signals here. You might have to look at a lot of Campi Flegrei interferograms to think that means anything. Sometimes they disappear. Sometimes you can see the same little subtle signals here, but nothing much to see. So how can we apply time series machine learning based methods to these data to have a bit more of a look at them? So a really quick synthetic example about how we could use blind signal separation methods. So you probably don't need to consider the top row too much unless you want to think about things in plots. But the key point here is that I could take a MOGI source, so some inflating deformation, and a noise term. So this would be a topographically correlated atmospheric phase screen. So this was a noise term that mimics topography and mimics the DEM. And that's quite common at a volcano, or really anywhere where you do InSAR and there's lots of topography. So that is a small curved mountain, and that gives us a big signal. So for this synthetic case, I can take these sources, mix them together, and I get synthetic interferograms. So these are a mixture. This one is dominated by atmosphere. This one is dominated by deformation. There's a little bit of atmosphere. And this one, again, is dominated by atmosphere with not much to see in terms of deformation. So what I, and also Susie Edmeyer, who's at the back, have spent a lot of time working on is how you can use machine learning methods. Given just these mixtures, can you come back to the original sources? So all we observe in our interferograms are the mixtures of deformation, atmosphere, and all kinds of noise terms. But can we somehow use machine learning methods to get back to our deformation sources or our atmospheric sources? So for this simple synthetic case, a very common machine learning method is principal component analysis. So principal component analysis would look to try and recover these sources that were mixed together to make our interferograms. And you can see that, well, it doesn't really work in this case. That one's mostly atmosphere, mostly deformation. It's not particularly convincing, and they definitely don't look like the original sources that went into our time series. But independent component analysis is a really cutting edge method. Well, perhaps not really cutting edge anymore, but it was 10 or 15 years ago. And it's still trickling through into the world of geodesy. So it made a big splash in MRI data. So there's always a lot of money in medical research, and it made a big splash when it was applied to fMRI data. So in our case, when you apply this to time series of interferograms, so observing just these mixtures, it does a really nice case of recovering just the deformation and the topographically correlated atmospheric phase screen. So just on the left, I've shown two examples of this, Susie's paper and one of my papers as well that talks about this in a lot more detail. It's quite a lot to pack into one figure, but if you want to read about it more, you can do. But the essence is interferograms are mixtures of signals, deformation signals, noise terms, and can we use machine learning to separate those back into their original parts? So as an example of this, our interferograms, which are mixtures, here are two University of Leeds staff. Any ideas? M2 is easy. That's Tim Wright. Does anyone know what M1 that mixture is? Who else is in there?
Well,
It's Andy, right? Well spotted. So if you use independent component analysis, giving it just these mixtures, these are what it comes out with. It's able to unmix them and recover them really crisply. So that's sort of a toy example of what we're trying to do here. We take our mixtures, and these algorithms can do better than some people in the room, but maybe not others. It depends how often you've seen Andy. So to do this, I've got a Python 3 package called LiCSAlert. So you can see we're building on the LiCSAR, LiCSBAS, LiCSAlert. So doing independent component analysis. If you've got a LiCSBAS time series, it should work really nicely with that to make it easy to use. So I think I'm going to show in my slides, I think I showed the example for 22D, and in the practical, we can do 24D, the other LiCSBAS track. So just showing it again, Campi Flegrei, some deformation, about 7 centimeters per year. When you apply independent component analysis to this time series, we get these sources out, which I'm showing on the top row. Sorry. So ordered by the Python package in terms of importance. So source 0, that looks like our deformation pattern. Source 1's a little trickier to interpret. I wouldn't like to say what that is. And I think source 2, again, looks a bit like the DEM. So that's correlated with topography. But if you want to do this analysis in a more interesting way, then the Python package will do the correlation between the source and the DEM. So you can see that for the deformation, there isn't really much of a correlation. There isn't really much of a correlation here. But this source, source 2, is really correlated with topography. So that helps us understand that this is probably a topographically correlated atmospheric phase screen, the kind of thing you see a lot of volcanoes. But what about in time? You could look at how these sources are used in time for interferograms at different baselines, so 200 days or 400 days. And in this case, you see that almost all these sources are not really correlated in time, but deformation, on the other hand, is correlated in time. If you have a 100-day interferogram, well, let's take a 1-year interferogram. If you've got a 1-year interferogram, you'd expect 7 centimeters of deformation. If you had a 2-year interferogram, that would double to 14 centimeters of deformation. And that's why you get really nice relations. So these would be the analysis tools for helping us understand what signals these sources that we recover are isolating. So we can't run this on Binder. It's a bit intensive, but if you were to run this, if you process your own data with LiCSBAS, you can download, install LiCSAlert from the GitHub, and you then get a full sort of interactive tool. So the point would be, I suppose, we've got our DEM here, so we can sort of see where we are. We've got areas of high topography. We've got our original time series that's processed by LiCSBAS. And then we can make a reconstruction using just the independent components. So for instance, if we have deformation and atmosphere, we can mix those back together to remake our interferograms, a sort of circular loop. Interferograms get broken down into components, and components can be recombined to give you your interferograms, but it's a sort of compressed version of them. And on the left, we just plot the residual here. So if you click on a point in this exploring tool, you can then see the time series of it, a bit like in LiCSBAS. So the point I think I'm taking here is that when we go back to the start of this animation, the cursor should move to, yep. So we're on the deforming region and you see a really clear deformation signal. If you then move the cursor up to an area of topography, you start to see a lot of atmosphere contributing, and that gives this sinusoidal seasonal variation. But IC3, which captures this signal, you can see there it is, that seasonal variation. You can click on that and turn it on and off. So sorry, loop back to the start, it's on. We can go through it once more. So start off with our deformation signal. Let's jump to somewhere where we get a lot of atmosphere. You get a lot of atmosphere, you see this seasonal variation, but then we can turn that off, which corrects our time series. Admittedly, it does underestimate it a little bit. It's not a perfect example. So you can rebuild your time series, and if you've isolated your noise, you can rebuild your time series without the noise. So I think I've shown 22D, but then there's a link here, so tiny.com/LiCSAlert2024, and that should open the 24D example. So can't quite have the full functionality of LiCSAlert in the little binder, but you should be able to run it, have a go at breaking a time series down into these component sources, and then recombining them to then remove sources that we term nuisance. So often for us, that's topographic correlated atmospheric phase signals. Yep, that was the solution. I'll just keep that hidden away. So that's the Sorry, it's opening a different window.
It's this one, I think.
Yeah. Oh, sorry, hang on. Yeah, that's right. Yeah.
Okay.
Is there can you see the Q&A? Is that anymore? Yes. So question, can we perform real-time monitoring using the reconstructed components taking the original one as reference? Short answer would be yes. That's what I spend most of my time doing, and that's why it's LiCSAlert, I suppose. So you can use it for a standalone analysis of a single volcano, but I look at how you can monitor how these components change through time as a way of doing volcano monitoring. Can you share again the link of LiCSAlert? Thanks. I think Pedro's just going to pop that in the chat for us. Thank you. So a second question, does the tutorial contain the tools that describe the ICE, I think that's ICA, describe the ICA method? So in this case, it doesn't, but if you wanted to run this in more detail, you could take the GitHub repository and run it locally, and you could see how the ICA algorithm works. In reality, the code is just a lot of lines of maths, which might make sense to somebody, but there's also lots of papers on ICA about how it works. So giving good demonstrations and using figures to demonstrate how the maths works.
That's a good question.
Yep.
How do you pick the reference points that you compare to?
In the interactive one that I showed in the slides, or in the example in the notebook?
Like just in general, yeah. Like in this example, for like why is it where it is? You know, is there something that you look for in particular when you have to pick a reference point, or?
Yeah, good question. So my easy approach would be that if you use LiCSAlert with a LiCSBAS directory of outputs, LiCSBAS will try and choose a reference pixel that's stable through time that you can reference your time series to. So my easy answer is that LiCSAlert just looks inside the LiCSBAS direction and finds that reference pixel. You don't have to do that, and you can move it around. So if I was looking for my own reference pixel, I would choose somewhere that I don't think is deforming, that I think is a good scatterer. So something quite stable, rocky ground, things like that. I'd also want to make sure there weren't unwrapping errors between where I'm interested in the deformation and where my reference pixel is. So I'd want a nice coherent path between my reference pixel and where it is. In terms of the other pixels that I pointed, such as the green and the orange one. So yeah, green is reference, sorry, so that's come from LiCSAlert. Orange, I've just chosen that because I've looked at the DM, which is in the previous part, and you can see that's an area of high topography. So lots of topography tends to give you these topographically correlated atmospheric phase screens. If I was doing this for a volcano I'm not familiar with, I would be using that interactive tool to click on a lot of different pixels and points and sort of have a look at how they behave through time, a bit like you could use the LiCSBAS tool to do. A second question. So the assumption is that the final product is not corrected for topography or atmosphere, and we are teasing out these components. Yeah, so I'm not an expert on LiCSBAS, but I know that LiCSBAS can try to reduce the atmosphere. So you can use Gaddes products, or you can try and do a correlation with phase against height for a pixel. So LiCSBAS would look at ways to reduce these terms, but often you're going to see time series that don't get rid of the atmosphere fully. And this would be also a bit location dependent. So if you had a small island, atmospheric corrections that come from weather models would probably be quite poor. And that's especially where something like this, a machine learning method, might work better. And then once we've taken this, you can then we can tease out these components. ICA would be teasing out these components, isolating your signal into different parts, and then discarding the ones that we are suspicious are noise. For anybody who's working through this, I think I will just show a few slides of the solution, and then people can play around with it at their own. I think if you're getting to the last cell, activity 5, there's a little area that's commented as editable. So if people are familiar with Python syntax, you could change which components, which time courses and independent components are being reconstructed to make our data again. So in this case, 0 to 5 are being used. So if I switch to Milan, was it LibreOffice you opened it with? Yeah, it was this one, wasn't it? Sorry, it's running on. What's your shortcut for start presentation on this slide? Shift F5.
Yes, maybe Shift F5. Let's try it because after.
Actually, maybe you can do it from right. So.
No.
It's one of those.
Yeah, there is not even any button, so I'm really not sure. 27 presses. Can I try?
Yeah, there is an option, right? But,
so many things. I'm sorry.
That's it.
Yeah, so let's try to shift it to F5. Oh,
yeah, perfect.
Yeah, okay.
So rather than showing those individual cells, I think I'll show a few slides showing the results. So on the left, you've got the LiCSAlert displacement. So one is in the deforming region. So you've got the uplift, about 7 centimeters per year. Our reference pixel, just a good sanity check, that should be 0 at all times. And then highlands, so that was the area of high topography. You could plot that through time, and you see this seasonal variation caused by changes in the atmosphere. So I think that what I'm trying to suggest here is that I don't believe this mountain is going up and down seasonally. It's a nice example because it's away from the deforming region, so you don't have uplift and atmosphere stamped on top of each other. In reality, over many years, it has 0 displacement, but it has an apparent movement of a couple of centimeters due to the atmosphere. And then on the right-hand side, we show how you can reconstruct the time series using the independent components. So if we use all our independent components, we should have learned an efficient encoding of the data. So our deformation components, our atmosphere components, and any other noise terms. And when you build them back together, you can check that the time series looks right. So the deformation is still there. The annual seasonal variation is there. The reference pixel does move a little bit now, a couple of millimeters. So that, yeah, a good sanity check that it's working and your input data is not just coming straight back at you. It's an approximation of the input time series. But with this approximation, because we've now isolated our atmospheric noise into one of our components, by changing those Python coding that I showed where you can select, in the example that was 0 to 5 chosen, we could choose instead to use, say, just one of the components, just the deformation component, and now you would clean your time series up to have something like this. If I reconstruct my entire time series using just the deformation component, then I still maintain my deformation pattern. So that was our 7 centimeters a year here. But because we've discarded that seasonally varying topographically correlated atmospheric phase screen, that pixel that initially appeared to be going up by a couple of centimeters and down by a couple of centimeters, up by a couple of centimeters, down by a couple of centimeters, is now stable, which I think is much more reasonable for that mountain. It's not in the deforming region. And what we were looking at was just atmospheric noise getting through the time series. So I think we're due to finish at 1:15, which is pretty close. Susie, did Tim say he'd like to come and say a few words to round up? Okay, in that case, if there's any last questions, are there any last questions on the on that part? So we had a question, why the reconstruction of reference pixel is not 0? Why there are residuals in the reconstruction? So in some ways it's a form of data compression and therefore it's not exact. So if you imagine a time series of say 200 epochs, so 200 times, so 200 times by 1,000 pixels, that would be a 200 by 1,000 matrix, so quite big. If you use ICA, you're going to compress that into a bunch of independent components, which would be about 1,000 pixels, and then time courses, which would be 200 long. So essentially, you're just taking the left-hand column and the top of your matrix. So you might be reducing the amount of data that you're storing by maybe a factor of 10. And if you've done that accurately, if your data truly can be expressed as just one of several components mixed together, that is an efficient and functional encoding, but it's not exact. And that's why your reference pixel might appear to move a little bit, and that's why there'll always be some residuals. So it would be better with a with a whiteboard, I could draw out the matrices and show how it works. But I think for a quick example, it's a very efficient encoding if you've done it correctly and if it works. And because it's an encoding, it's not exact. It's a sort of lossy compression, and therefore you tend to see a little bit of movement on the reference pixel and some residuals in the reconstruction. If there's no more questions, anybody in the room, then I'll hand over to Milan and Susie for the concluding remarks.
Thanks.
Oh, but there is one more question. But that's, yeah, okay. Yeah, great, awesome. All right, so some short word at the end from my side. This is the end. Thank you very much.